So we are back and our model has been trained on our training data, and let's just try to understand what this output shows. So it tells us that our data has been trained in 10 epochs, and uh, we get the output of loss accuracy, validation loss, and validation accuracy. So loss simply signifies that how far the output of the model was from the actual expected value. So and the accuracy tells us how accurate it predicted the output. And then the validation loss and the validation accuracy is for the validation data. So we'll understand this when we'll plot it using a using library matplotlib library. So we'll understand it better. So after we have trained our data, we can try to look at how it the summary of the model. So we understand what our model actually consists of. Okay, so it gives us the summary that it is a sequential model and it has 1, 2, 3, 4, 5, 6, 7, 8 layers. So the first layer, none, this is for the batch size, and because we haven't mentioned any, it says none. So the first layer, this is giving us the output shade. The output from our first layer is 30 by 30 and 32. 32 means we have 32 feature maps. That means the first layer uh, computed 32 different feature maps from the image, and each of the feature map size has the size 30 by 30, which is less than the actual size, which was 32 by 32. And this can happen because there might be some pixels that were not grouped properly, so the model had to skip them. So it is possible, and those were at edges, so it won't impact our output really much. So it has total 896 parameters that can be trained, that can be every time our model learns, we can optimize these parameters, can be optimized and trained. And then we have the max pooling layer. So it basically reduced the size of our image. That was feature map, size of a feature map that was 30 by 30. It reduced the size by 15, and now it is 15 by 15. And then again we have 32 feature maps. Then comes our next layer, and even next layer gives us an image output of 13 by 13. Again it reduces the actual image by actual value by 2. It changes it by 2. It was 15, now it is 13, again for the same reason. And we have total 64 such values because this layer had 64 features, so it generated 64 different values. Then we again have the max pooling layer. It again reduced the size of the feature maps to 6 by 6. Again 64 was the number of values that were the number of values that were output by this. Then again we have the convolutional layer, and the size again reduced by 2, and again we have 64. Then we have the flattened layer. So what it does, it combine all three of them, and if we multiply 4 by 4 and 64, it is 1024. So it combined all of these values, all of the 3D values, into a 1D value. And when then one we have now we have a one-dimensional array. Then we have the dense layer. So dense layer, we have 64 values out of the dense layer, because we are again going to focus on 64 main features that we extracted, that was learned during the process of the image processing of the model. So we are going to have 64 output from this layer, or you say 64 nodes, and then each of the 64 nodes are going to be connected to each other to produce an output for the last layer, which is the dense layer. And it has 10 values because each value corresponds to each class in our data set. That means from That means each value corresponding will be corresponding to airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck, and we will generate 10 outputs from this, and the maximum value will be considered as the final output. For example, if we have the value for airplane, the maximum value for airplane, then it will be considered as the image belongs to the class of airplane. So, okay, now let's evaluate our model. And by evaluating our model, we mean that we want to see that how the model is actually performing. So for that, we will define two variables, test loss, comma, test accuracy, and we'll say model dot evaluate, and we will give our data that we want to evaluate, on the basis of which we want to evaluate a model. Here we are using the same data that we have used for validation, so it will not uh, be very significant, but I just want to show you that how we evaluate a model. So this is going to take the test data, and it is going to try to predict the values for the test data, and then it is going to compare those values with the actual expected values, and it is going to see that how the model performed by giving us the accuracy and the loss, which will denote that whether how well our model performing. So let's try to print this. So if we run this, now it is evaluating a model, and okay, so it gave us a loss of 0.9515 and an accuracy of 0.6945. These output does not signify that our model is performing really well, because we might need to do a lot of things on the top of this model to improve it, but this is just the fundamentals. So let's just go with the flow and see what we have to do next. Next, we can plot the training history, and from the training history we will able to see that um, while the model was training, how was it improving over each epoch while it was training on different data, in each epoch, how it was improving. So to plot the model, we'll use the uh, library pyplot from matplotlib. So let's see how we do it. So let's see what we have done. So we call the plot function, and we are going to plot um, our accuracy matrix, and we are going to label it as accuracy, and then we are going to plot our validation accuracy matrix, and then we labeled it with the word valuation accuracy. Then we have defined the X labels and the Y labels, and we have defined that where the legend should show, it is should be in the lower right, and then we show the plot. And after showing, here we can see that this is our accuracy and this is our validation accuracy. So we see over time, as the model trains, the accuracy has been increasing. So it increased from 0 to it increased from 0.45 to around 0.80. So accuracy increased, but the validation accuracy, we see that it was first improving and then it was steady. So this is how our accuracy looks like over time. Now the final step, we can try to test a model, which means that we can feed a input to the model that we have trained, and we can see that how the output is generated from it. So in order to test the model, we will have to first, let's take an image. Let's take an image from X test, because that is our testing data. So let's take any image. Let's say 17. We can try to, if I want to see how what the image is, we can use plot that I am show, and just see the image. So Of course, these images are really blurry, but it works for the model. So this is the horse. So let's see if our model is able to predict whether this is a horse or not. So for that, we will have, let's first see that what is the shape of our. So let's see what is the shape of our image. So the shape is 32 by 32 by 3, but this is not the shape in which our model accepts the input. It accepts it in 4 dimensions. So we are going to reshape our image before we feed it to the model. So we are just going to mention one another parameter, that is the batch size, because it is only a single image. So we'll pass one so that it understands this is going to be a single image. So let's put it into another variable, and we have done this. Then we can predict our class to which the image belongs to. So in order to do that, we'll call the predict function from the sequential API. So we'll just pass the uh, pass the image to it, and then so we're just going to pass the image to it. So it is going to produce 10 outputs, but we want to see only the one that is the highest. So we will write that give us the give us the output that is the max out of all the values that are predicted. It is going to predict 10 values. Give us the value that is the max. So it will give us the predicted class. So let's see if it is able to do this. Mm, what have I done wrong? Brackets. So our predicted class is 7. So let's see what does 7 signify. So 0, 1, 2, 3, 4, 5, 6, 7. 7 is horse. That means our model is able to accurately predict the class. So that means our model is not doing that bad, but it was also not that good. So we have to change a lot of things if in order to make it really efficient. But the goal that was to be covered with this tutorial was only to cover the fundamentals, and that has been done. Let's review what we have done. So we understood what are the libraries that we will be using for an image classification task. So how loading and pre-processing the dataset. So we pre-process the dataset by normalizing it by dividing by 255. Then we define the architecture of the neural network with 8 layers and using the sequential model. And then we compile the model, which determines the optimizer, the loss function, and the metrics that we want to use with this model. Then we train the model using the fit function. We feed into our training data and the validation data to evaluate the metrics of the loss and the accuracy of the model training. Then we summarized our model to understand the architecture. Then we evaluated our model by passing the testing data to it, and printing the loss and the accuracy, how it is performing. We plot the training history, which helped us understand that how our model was improving or whether it was improving or not. And then at last we tested the model just to see that if our model was being able to predict and how it was going to output. So from this it is clear that it is producing outputs in integer values. So it is going to produce integer for each of the class, for this 0, 1, 2, 3. So it is going to produce integer for each, and then we can obviously convert this integer, map these integers to their particular class by defining the labels and then printing it. So that was all. I hope you enjoyed it, and let me know in the comments whether you like it or not. I will also mention the source code for this because I have put that to my GitHub repo. So I will post a link in the caption below. If you want to check it out, you can. Please subscribe, share, and like and support. Thank you.